So I think maybe let me redraw this again. So last week we talked about, last Wednesday we talked about attention. And today we're going to talk about some variants of attention, some of the details, how to improve it a little bit here and there. We are not going to go into all the details because it's a very actually complicated field. You probably have seen Samaran's talk, and that's also just the overview of this area. Actually, there's a lot of co-design of the architecture with some of the properties of the GPUs. We cannot really go into all the details, but I'm going to give you some kind of like feeling about what people can optimize for the architecture. And then after that, we're going to move on to a few other kind of like things related to transformers. One thing is that how do you do the few shot learning with in-context learning. Another one is like the zero shot. So basically these are about how to use large language models with few shot learning, zero shot learning, and one thing is like the SFT, how do you fine-tune the large language model, so on and so forth. The rest of the lectures are a bunch of small topics which are pretty kind of almost trivial, but I have to mention all of them in some sense to clarify the concept. But they are relatively easy stuff after I talk about architecture. Okay, so, and I think I want to review the architecture a little bit quickly for 5 minutes, just to remind you what is the transformer very quickly, because what I'm going to talk about depends on those. So let me redraw this figure. So last week we talked about this queries, keys, and values, right? These are the core of the attention in the transformer. And recall that, if you have a single head in the transformer, you have this Q1 up to Qt. This in a time dimension. For each time step, you have a query vector. For each time step, you have a key vector. And you also have a value vectors for each time step up to Vt. And this is only for a single head. And the attention means like you take some inner products between this, right? So, and you compute some softmax, right? So that means that you say, and also we have the autoregressive model, which means that you never attend to things that happens after you. So you always attend to the past so that you can have the autoregressive nature. So basically Q1 attends to K1, and the Q2 will attend to K1 and K2, right? And Qt will attend to all of the things before time t, right? Something like this. So basically the connections here are pretty much like it's a kind of like, if you visualize it as a matrix, it's the upper triangular matrix. So you only have like attentions on the left, but roughly speaking, you have half of the edges, right? And then once you get the attention score, you multiply them with the v's to get the final outputs, right? Something like you have a matrix Q, which is like you have Q1 up to Qt, and you have a matrix K, which is K1 up to KT, and you also have a matrix V, which is V1 up to Vt, and the formula was something like Q times K transpose, which is the inner product between this, and you add a mask to make those kind of like invalid kind of like attentions, minus infinity, so you don't really use them, and then you do a softmax, and this is a row-wise softmax, and then you multiply by the matrix V, something like this. Right, that was what we discussed for one single head. And then when you have multiple heads, what you do? When you have multiple heads, what happens is that you have many replicas of these kind of things, right? So you say, as opposed to just only one tuplet here, right? This is one head. You have another head, which is not a replication, but it's the same architecture with different weights. So you have a Q1, say 2. Let's use 2 to indicate the second head, and you have Qt2 and K12 up to KT2 and the V12 up to VT2. And then you can have 3 and 4, so on and so forth. You have a number of these heads, right? And this is maybe Q11, Q21, so on and so forth. And you have many of this kind of like attention head. Okay, so, and I think in the last 5 minutes of the last lecture, so we also discussed some of this kind of like the efficiency perspective here, right? So I guess the computation here is t by t, so you have t squared at least scales in t squared in terms of the computation. And in terms of storage or memory, you have to linearly scale in t, because the larger the t is, you have to store more things, right? All the q, k, v in your memory. So actually, you only have to store the k and v. You don't have to store the q, because as you are generating more and more, you can drop some of these q's in the generation process, because only the q's for the last step is needed, but the k's for all the previous steps is needed when you generate more and more. But in any case, just the k and v requires linear in t memory, and that's why it's called kv cache. I guess probably have heard of this word. So basically, you have to save all the k's and v's for every head in the memory. And this is a huge storage space. Basically, this restricts, from a system perspective, the details is more complicated, but let me give you the high-level thing. So because you have to save all of this, they take a lot of memory in the GPU memory, and that makes it very hard for you to have a lot of examples in your batch, a lot of sequences in your batch. So in some cases, even just saving the KV cache for the one single sequence will use up most of your memory. Or maybe you can use probably you can save 10 sequences or maybe 100 sequences, something like that. But there's a limit on how many sequences you can save. In your memory. So basically, you cannot have a large batch size when you do the inference, because there's not enough memory to save all of the KV cache for all of the sequences. And when you don't have enough large batch size, then you have this issue with the arithmetic intensity that Samuel talked about a little bit last time. So basically, you cannot leverage enough parallelism across different examples to utilize your GPU compute. So basically, you are bounded by the memory, and you cannot use up all the GPU's compute. So if you measure the throughput, or there's some quantity called MFU, I think Samuel introduced last time. So basically, your GPU is going to kind of bounded by the memory, and it's waiting for work for the compute side. So that's kind of the dependency here. So and that's why people thought it's probably very useful. It's very useful to reduce the amount of KV cache you have to save here, right? We are saving too much KV cache in the memory, and that's why there's so-called group query attention, which is introduced by the Kun models and DeepSeek models. So group query attention. And the way to do it is that you say, I'm not going to have all the different kind of I don't have that many keys. I'm going to reduce the number of keys, but keep the same number of queries. So basically, this is the head ID, right? Head 1, head 2, so on and so forth. I have so before I have for every head, I have different keys and values. And now I'm going to have some kind of shared kind of keys and values across all the heads. So what happens is that you have, in the time dimension, we cannot save much. So that's kind of not a question, right? So it's more in the key and query dimension. So basically, you say you have Q11 up to Q1t, and then you have Q12 up to Q2t. This is the first head, this is the second head, maybe you have the third head, so on and so forth. But on the key side, you have much fewer groups of the keys. So you say, I have so maybe here is a 1, 2, 3 up to NH. This is the number of heads. But the number of keys is much smaller. So you say, I'm gonna have a few group of keys. So this is maybe let me draw this. So I have key 1, 1 up to key 1, T1. This is the first key and sequence of keys. And maybe let's just say I have 2 sequence of keys. Okay, maybe let's use a generic. So let's say K1, say, I think NG, and KTNG. So I have NG group of keys, or NG sequence of keys, but here I have an H sequence of queries. So maybe the last one here is Q1, 1 up to QTNH. And NH is bigger than NG. The number of heads bigger than the number of groups. And often you just make the NG divide NH so that they are kind of you can have a even distribution. And what you do is you say, it was supposed to be that one key set of keys is paired with one set of queries, but now you group them. You say this maybe two set of keys is also both matching to attending to this set of keys. So so basically I'm gonna say that, let's say suppose NH is equals to tau times NG, and tau sequences of the queries will match to one sequence of the keys, because you have tau multiplier, tau factors of more keys. So that's basically, it means that for these queries and for this queries, you're going to use the same set of keys when you do the softmax. And the same thing for the values. So basically, once you have the attention matrix, and then you apply to the values. So basically, the number of values is also the same as the number of keys. That's how you do it. So basically, in some sense, like you are drawing. If I have to draw the inner product, I'm going to do this, right? So, and this one will also attend to this, and these queries will attend to all of this. Does conceptually make sense?
Is 2, so tau will be equal to 2.
Tau will be equals to NH divided by 2. So if NG is 2, as I draw here, I have only two groups. So then,
and if NH is 4, that's just...
then tau is also 2. But if NH is like 100, then tau will be 50.
Right, and that means every 50 of these heads are going to map to one of the keys.
Yes, exactly. So mathematically, I think I can write them, but I don't think necessarily mathematically it really makes things easier. I think visually is probably the easiest. But anyway, let me try to just quickly write down the mathematical equations. So just in case this is helpful for some other people. So I think one way to write it is that you say you have a sequence of like a query matrix. So this is like for each of these query matrix is kind of like one sequence here, and you group them into a matrix. So you say Q1j up to Qtj. In this dimension is the time, and j is indexing which set of queries you have. And so j is from 1 to nh. And for keys, you have much fewer keys. So you say you have K1s up to KTs, but S is from 1 to NG. And the same thing for V. You have V1s up to VTs, and S is from 1 to NG. And then you define some mapping, between how to use the more queries with the keys, right? So you say, for the J's query, you say this is mapped to GJ, which is defined to be this. Is this some echoing? Okay, +1. Did you hear it?
Yes.
Okay, I guess. Okay, anyway, let's keep going and see. So tau is the difference between these two, right? So basically, j minus 1 divided by tau is kind of like which kind of like set of keys you are mapping to, and floor plus 1. So this is a number between 1 and ng, right? So basically, you're saying which group I'm in for this query j. J is in 1 to nh. So, and then once you know which group you belong to, and then you can do the inner product. So Qj will be multiplied inner product with Gj transpose, where this is the index for the group for the keys you have to attend to, and then you divide by C. This is the normalization constant, and you multiply by m, and you take a softmax. And then you multiply by VGJ, use the same ID for the set of values, and this is the output for the j's head. So you still have the same number of heads, same number of outputs. It's just like some of these outputs are using the same k. So that's the only difference. Did I explain the C last time? The reason why we have a C is because we want to make sure the input to the softmax is kind of like more normalized. So C is often chosen to be something like, so this is a matrix like this inner product, no matter whether you have the GJ or whether you have the group chorus or the standard multi-head attention. This inner product is always something like is a T by kind of like DH and DH by T matrix. So basically each entry is inner product of two vectors of dimension DH. And typically C is chosen to be something like square root DH. And that's because if you have, suppose these two matrices are on the order of like +1, -1, then the inner product between two vectors, so you have two vectors, they are of dimension DH, and you take the inner product, most likely if they are random, then they are all on the order of like square root DH. So suppose you have like two vectors, maybe say A, which is on the order of like, which is of dimension DH, and B is on a dimension DH, and they are somewhat random, and each of the entries of A is on the order of +1, -1. Let's say each of the A sub I is kind of like on the order of like +1, -1. Then the inner product between A and B, right? This is on the order of like a square root DH. So, and if you choose C to be DH, then you will cancel out with this scale so that it becomes back to the scale of 1, so that it doesn't depend on the dimension as much. Right, so ideally, you want to make sure that even you change dimension DH, you don't have to change your architecture too much. Right, everything is on the right scale. So that's why typically people choose C equals DH, square root DH, so that you can cancel with this scale. Of course, this is a very heuristic kind of like a calculation. There are, for many kind of cases of this kind of normalization constant, there are different theories which can give you slightly different kind of like predictions on what's the right way to do it. For example, depending on how you think about the A and B, right? Why A and B should be random-like, right? Maybe A and B should be all kind of like already in one direction in some sense. Then you should choose a different normalizing constant. Empirically, it sounds like this normalizing constant, at least is one of the working choice. Other people probably use other choices. But generally speaking, the choice here is kind of like you can only have some heuristics to justify it, but it's not like it's not like you can really rigorously predict what's the right thing. So like you have some intuitions, you have some heuristics, and then you try it, and empirically it works, then that's your choice. Okay, sounds good. Any questions so far?
Any specific reason why you chose to group queries instead of keys and...
Oh yeah, that reason is pretty clear because the queries doesn't have to be stored in your generation. So basically, if you're at time t, you only have to store the query at time t. In the pre-filling, or training, you have to have all of them. But I think we're mostly thinking about the generation time. So in the generation time, at the particular time t, you don't have to use any of the previous queries because you already computed the query to the key attention for those queries already. So you don't have to save the last query, right? So that means that the query storage or the query, the memory cost for query is much smaller than the memory cost for keys and values because you have to save the whole sequence. Yeah. So that's why you have much more incentive to reduce the number of keys and values. And of course, you can kind of like universally reduce all of them, but then you are just trying to reduce the number of heads in some sense, right? Yeah.
What's happening on that bottom right board in the middle of this?
Which part? Sorry. This one?
Yeah.
This is just trying to formalize how to compute the coordinates and key attention. So like in matrix form, so in some sense the high level overview is that figure. So basically you do this Q, J, and K. The G parenthesis J is what you are, which group you are attending to, right? So for for both this set of queries and this set of queries, you are turning to this set of keys. So that's the index for G, this index. And then the Q and K inner product are the inner products between the keys and queries. And then you mask it, as we discussed last time, and you take the softmax and you do the normal attention. Yeah.
I think the only thing that's different is that we can now attempt to different groups of keys.
Yes, we have fewer number of keys, fewer sets of keys, and different set of queries can attend to the same set of keys. Yeah.
So in the previous when we had the last one, it was that within each of the heads, the keys were different.
Yes. So basically, you have so many different keys here. Yeah. Good.
How do you select the value of tau?
The value of where's tau? Oh, tau is here. This is just a parameter. I think. So, you can, there are three numbers here, right? So, I guess you just, you have to respect this equation. Other than that, you just choose something that works empirically. Of course, if you make tau too big, so for example, tau can be equal to NH. Then you just have only one set of queries, one set of keys and values. Then you have the smallest possible memory cost. But the problem is that you store too little in some sense, right? If you just only have one set of keys, then maybe you don't have enough information stored so that you lose some of the information of the past, right? Because in some sense, how much you store depends on a little bit on, the storage is needed in some sense because the memory is needed because you have to remember what happened in the history, right? It's more like how much you have to remember is something you need to kind of tune in some sense. So I think actually this is a good question in the sense that I think if you choose tau to be the same as NH, so that NG is 1, I think this is called multi-query attention. So basically the history is that, and there was one paper that actually chose this, and that paper is the first paper along this line. And then later on people say, oh, this is too aggressive, like you have to actually do have some number of keys and don't be that aggressive to have only one key. So that's why they start to use bigger NG. I don't know off the top of my head how big the NG is, maybe like 100 or something, maybe, actually I don't exactly know. Maybe we need to check the code. Yeah.
When we're defining which Q goes to which log of case, it's kind of monotone. It's like we have like first some Qs go to the first K, and then like the next ones. Is that like ground loss, or like is there any meaningful in like the order of the heads? Or
the order doesn't really matter because anyway all of these are learned, right? So whatever order you do, as long as they're kind of like a topologically equivalent to each other, because anyway these keys are not something you design yourself. You actually have to learn the right keys, right? Suppose I permute this dependency thing, then the training code will permute that as well to accommodate. So of course, you can ask whether you should do something like 2 queries match to, 3 queries match to 2 keys. Do you have to make it like a tree structure, like a one key for many? Is that like a one key for many queries, or it could be like a one queries also get to 2 keys? I don't think people have tried that yet. And another thing is that this structure, to some degree, cannot be too dynamic because you have to, in some sense, you have to hard code it on the GPU so that you can really run it very, very fast, right? So you have to exactly know which one you compute in some sense, so that you can compile it so that you can run it on GPU. So I think empirically, actually, people just really do literally what I'm doing here, so that actually you also have some locality stuff. Like for example, you probably should put these kind of things closer to this in some sense. And also empirically, I guess you actually could, very likely you could, depending on the situations, you could put this key and the corresponding queries into one GPU card, and then this key with the corresponding other queries into another GPU card, so they can reduce the communication, all of those.
That last lecture, but I was a little bit confused on the queries and the keys. Are they intuitively, it seems like what they're doing is trying to figure out, like, if I have a current word, how related is it to another word? So would that mean that the Q and the K, they're both morally dependent on their own word and not really on the other words?
I think that's, I think on the word level it's probably too granular. I think, I think at least it depends on the nearby words as well. Yeah. But the intuition doesn't, anyway, it's kind of like intuition. I think it's about right. Yeah. Any other questions? Okay, so now let's talk about another variant of attention, which is trying to deal with a different type of issues. Sorry, I need to type. Okay, I don't need it. So another variant is so-called like sliding window attention. So this is for a different issue with attention, also with some system perspective in mind. So if you think about this, right, so we talk about the memory a lot, right? So, but if you think about the compute, it's also an issue, right? Because you have to compute this pairwise inner product between T and T sequence of vectors. So that's T square computation. And when T is big, that is quadratic, and you can really get into trouble. For example, if T is 1,000,000, then 1,000,000 square is really a big number, right? So you have to find some ways to make it not quadratic dependencies. We don't know exactly how the frontier labs are doing this, but at least one way people have done in the open source community is that you just don't compute all of these attentions. What you do is you just say you have a sliding window so that you only have to attend to some amount, like some recent history. So suppose you have Q1 up to Qt, and then here you have K1 up to Kt. And you say Qt only attends to the last W positions. So, and W is the window size. And then Qt minus 1 attends to this one and, attend to the last W as well. And Qt minus 2 attends to the last W. So basically, there's a sliding window that depends on where your query is at. And you can see the limitation here is that your attention is very limited to only the recent tokens. Of course, it's not like these recent tokens just only about, it's not exactly true that let's say this is like a Kt minus W, right? So it's not exactly true that this W positions are only about the last W tokens. That's not entirely true because this keys also depends on what happens in the layer below. And the layer below can attend to even earlier tokens, and the layer below can attend to even earlier tokens, right? So if you think about there are multiple layers, then if this is the top layer, then the top layer attends to the last W positions, and then this key eventually depends on some hidden vectors, which we discussed. It's a projection matrix of the hidden vectors, and that hidden vectors probably depends on the previous W. Will depend on previous W tokens in the layer below. And then you have this kind of dependencies like this. So basically, depending on how many layers you have, you can look back in theory for quite a number of kind of like tokens. So let's say suppose you have like IO layers, then you can look back for IO times W tokens. And that's the limit. After that, you have no dependencies on the previous tokens. So that's the limitation. Like you can at most look back for L times W tokens. And in some sense, you're going to forget about some of the past if you have if the T is big enough. So that's a issue. But if you are doing this, then you can save the compute because it's no longer T by T attention. It's going to be T by W because each of the cores only have to attend to W vectors. So it's T by W and it's linear in T as opposed to quadratic in T. Yeah, but I don't think this is the only, you cannot just do only this. If you only do this, you're going to have some issues with the the forgetting of the long context. Eventually, you're going to forget about the past. There are many papers that discuss how to have other ways of this sparse attention that don't forget about the past. We don't exactly know which one is the best yet. I think in the lecture notes I did set some papers. If you are interested, you can read them. Okay, and maybe one more small component. Just there are many more details here I can discuss. Just in the interest of time, I can only select a few that I feel somewhat interesting. So another small detail here is relating to this thing that I talk about the C, the normalization. So here, if you think about it, so this assumption that each of the AIs are kind of on order of 1 is kind of like not quite guaranteed, because if you train it, then eventually sometimes maybe A and B becomes bigger or smaller. So one way people do is that people actually normalize this A before taking inner product as well. So for example, you can say, as opposed to taking, so before you are taking Qj times K, say KT transpose, right, divide by C, what you can do is you can also normalize Q and J before that. You can say you can do RMS norm of Q, J, times, some normalization of KT transpose divided by C. So that, before you go into this inner product, you are somewhat normalized, and then you can stay on the same scale for most of the cases. Again, this is a heuristic, but people do use this in some of the open source models. Okay, so the next part about architecture is mixture of experts, but before that, any other questions? Yep. Yes. Yeah. T and W, yes. But W is often much smaller than T. It's kind of like a constant to some degree. It's not exactly right, but so basically your computation is T times W now, as opposed to versus T squared before. And W is a small number often. The length of the window you choose in this option. It's a new parameter you choose. And you choose the window to be, for example, 1,000 tokens, then no matter how large T is, you pay T times 1,000. Any other questions? Great. Okay. So these are all about attentions, right? So there's another part, which we discussed, but we didn't discuss in detail, which is the MLP, the fully connecting networks part. Right? We call that, the transformer is actually a combination of like attentions and some kind of like MLP, multi-layer perception, which is the same thing as fully connecting networks. I guess MLP is the same as FFN. It's just that they are interchangeable. And you have these independent MLPs. And then you do attentions, right? This is the general architecture of the transformer. So now let's talk about MLP part. So for the MLP part, you could also try to scale. So the MLP, as we know, like is the network, right? You have some kind of like matrix application, right? So if you just scale the dimension, then it's fun, but you're just gonna increase your compute time and your memory time, right? So suppose you have a D by D matrix, and if you say you double it, you're gonna make your compute 4x, and you're gonna make your memory 2x. So and that's one of the ways to scale. However, I think what people found out is that you can actually scale in a more kind of like parallel way in some cases. So the idea is that instead of computing a big gigantic matrix, so you can, the default is to have some vector v, and you multiply a big matrix, a D by D matrix, and you output a vector v, you maybe output a vector O, right? So and for this mix of expert ideas, what you do is you say you don't do this, but you have an input v, and you decide you have a bunch of so-called experts, E1, E2, so on and so forth, say EK, and you decide which subnetworks you send to, and then each of these EI is MLP. and then you aggregate. Actually, the aggregation is just some average. You get a vector. You get an output. And what happens here is that you have so many experts. You don't choose all of them all the time. For different input, you can choose, or for different tokens, you choose different experts. So actually, what really happens is that you have input vector v. You have a routing module to decide which one it routes to. And you only route to a subset of them. You route to, for example, this one, and maybe this one, let's say. And for the other ones, they just exist there, but you don't use them. So what happens is that now you can disentangle the memory and the compute in the sense that you have a big memory, or you have a big number of parameters because you have like a lot of this component EIs, but the number of active ones in each of the actual compute is probably a smaller number. For example, the number of actives, say, can be 8, but the number of total experts maybe is 128. So basically, you have 128 experts, which are all sitting in the memory somewhere. And each time when you compute, you only take a subset of them. So there are several kind of like intuitions on how do you, why this is useful. One intuition is like what I said. So this way, you can add more and more experts without, you can get more parameters without changing the computation much, right? You can have like a trillion parameter model with a lot of experts in it, but the active number of parameters is smaller. So that's why in this stage, if you rate some of these large open source models, the way that people do it is they don't say it's a 70B model. They say it's a 30B, A3B, right? I'm not sure you have seen these kind of things like 30B, A3B. I think that's A3B. So what this means is that there are 30B total parameters. If you count all the parameters and experts, you have 30B. And A3B means active 3B. It means that when you actually do the inference, do the computation, only 3B of the parameters will be activated, and all of the other ones are not used. Of course, those kind of modules can be used for other tokens as well, but for this particular token or particular position, you don't use all of them. And another original motivation for mix of expert without a system perspective is that you somehow believe that each of these experts are doing different, having different specializations. For example, maybe expert 1 is about math, and expert 2 is about physics, and expert 3 is about the common English language. Expert 4 is about coding, so on and so forth. And so then for each of the tokens, you execute different experts for specialization. So in some sense, you specialize to different things, and that's probably better for efficiency because specialized networks can be smaller, and you still get the same performance gain.
How you train them to be specialized, but I guess you just train them on specialized.
You don't really train them to be specialized explicitly, but they could possibly naturally become specialized because that's the most efficient way to do it, right? So like if they are all general purpose, then maybe that's not the best way to minimize the loss function. I think there are papers that study how specialized they are. I think how specialized they are depends a little bit on your definition of specialization and how do you interpret the results. But I think at least I've read a few papers which claim that the specialization is pretty strong in the networks. But on the other hand, if you really think about it, right, for the same sequence, you still send to. So this thing is not okay. Maybe one important clarification is that it's not true that you decide experts for each sequence. You decide experts for each token and each layer. So each position, each layer. So for each layer, you have like a sequence, right? You have a lot of MLPs, right? And this is like a time dimension, right? Like 1, 2, 3, 4 up to T. And for each of these MLP, you decide which expert you use. And for each layer, you have to decide again. It's not like even specialized only to specific to only the positions, but also specific to positions and layers. So in some sense, it's not entirely clear how much specialization you can do here, because in some sense, for one sequence, maybe it's always about math, right? So, and empirically, you do see that the number of experts you are running is smaller than the total number of experts for each of the sequence. But I think that the numbers is not like very sharp. It's not like for one sequence about math, all the experts are the same, the math expert, not exactly like that.
on specific things? Because you said that you don't explicitly train them.
So you want to explicitly train it. I think some people have tried it. It doesn't seem to work as well as end-to-end training. And also you don't really know how to train them specifically, because how do you train each of these experts, right? So are you training them on different data, and then you have not enough data. Sometimes you have enough data for math. So it's much more cumbersome to force the specialization to some degree. Yeah, I think, but we don't know. I think it's possible that some people are training that. It also depends on what's the granularity of this, right? So for example, if you just only have 8 experts and each time you choose one, I think maybe there's a good reason to, at least it sounds more plausible to train 8 of them separately and then try to aggregate. I'm not saying people have done it. At least I don't see public papers people have done this successfully very well, but it sounds at least plausible. But if you have 258 experts, right, and each time you choose 8 of them, it becomes much harder to decide a priori how do you choose that 256 experts one by one, right, in some sense. Okay, so
this choosing part, how is that decided? Is that decided?
Yeah. I haven't talked about that. Yeah, that's a great question. Yes, let me talk about that. So how do we choose? So the choice, the routing is decided by the numeric groups as well. So the routing is decided by often a relatively small routing module. There are different design choices here, but let me just show you one particular ones. So let's say we have an input, and maybe more mathematical. This is the input, is the vector v I'm talking about here. So the input of this is some hidden vectors in the transformer, and then you first do a routing. You say you compute something like this: sigma ht times a routing matrix, and you make it the output is equals to is a vector of dimension m, and say m is equals to the number of total experts. So you project your inputs to some m-dimensional vector, and you apply some sigmoid can be softmax, or the sigma can be softmax or sigmoid or something like that, so that you get an m-dimensional vector, which is the kind of the relative importance between all the m choice of experts, and then you take often you choose a subset, right? You choose st to be the largest indices of RT. So among these m dimensions, you choose a subset of, I think maybe I should just remove the t, because the t is irrelevant here. That's my bad. So basically, R is a vector of dimension m, and you choose the largest entries of R, and that's the set S. And how large it is, how large S is, this is, S is the number of active experts. So for example, S could be 8 and M could be 128, something like that. And then once you choose the largest indices of the largest set of indices of R, let's say this is like the k largest, so this is equal to k. So and then you say I'm gonna run my expert on this input. So I'm gonna run E of S on the input H for S is in capital S. So capital S is my indices of the k largest, and I'm gonna run for each of the S in the k largest. I'm gonna run the expert to get some output. And then I'm going to weight all of these outputs. Right, so I compute this, and then I'm going to, the final output of this module is going to be a weighted sum where S is in this. And what's the weight? the weight it needs to be summed to 1, and the weight is often just a renormalization of the R. So the weight RS is just renormalization of R. The alpha S is renormalization of the R's. So you sum up all the R's and you renormalize it so that it becomes a norm 1. Oh, actually, this is, you sum up, yeah, my bad. This is actually small nuances. Not that important, but let me correct it. So you are summing up all the weights in the selected subset, so that among the set S, the norm of the sum of the alpha is equal to 1. So this way you don't change the scale too much, right? Like you are taking a convex combination of these outputs, with the coefficient summing up to 1, so you don't change the scale too much. And one more small thing is that sometimes people also have so-called shared experts, meaning that among all of these, maybe I should use M here. So among the M experts, some of them is always used forever, like for every position, every layer. So you say you reserve one that is always used, and then the rest of them are selected like this way. That at least that's one of the, I think in DeepSeek v3, that's the design choice. And I think the rationale according to the paper was that the shared expert is kind of like something about common knowledge about English, for example, or the language. And every token needs to use that. Every position, every token needs to use that. And then the rest of them are about specialization. I don't, for sure, they use it for a reason, right? But I think there are also other models which don't use this design as well. So, yeah. And generally, people try to make sure all the experts are used equally in some sense. So this is actually, I didn't discuss the training, which is actually very complicated for, at least it's very subtle for MOE. One of the challenges to how to make the MOE training work. And in the training, often there are some regularizations on how the routing is done. So basically, you want the routing to be as uniformly distributed as possible. And part of the reason is that, for example, in a dream case, right? Suppose the routing is always routing to some two experts, but not any of the other experts. Then you are wasting your memory to store all the other experts, right? So and your effective model size is not big enough, because if you only use the first two and all the others are not used, then effectively your model is actually smaller than the parameter counts, and that shouldn't be efficient. So people try to add regularizations to make the routing more uniform. Another thing is that if the routing is not uniform enough, then it's also a little bit hard to design your infrastructure to deal with it. So basically each of these experts on different cards, suppose there's too much heterogeneity there, then some cards are not used enough compared to the other cards. So then your efficiency in the inference is not good enough. Of course, there are other ways to deal with that. For example, you can provision more GPUs for one of the experts than the other experts. I think actually, I think in one of the DeepSeek paper, they even say that they have a dynamical way to change how many GPUs are used for each of the experts. For example, in the US daytime, some of the experts becomes more often used, and then they provision more GPUs for them. And then the China time, because I think most likely because of the language, right, or kind of the use cases shift, then some of the other experts becomes more activated and more used, and then they provision more GPUs for those kind of experts. I don't know whether that's exactly the case, in all of the models, but that was what's reported in some of the papers and blog posts.
Quick question. So, we've been having the economics are expert because it's more efficient on the GPU, correct? Or was there some other reason? Actually, this is using a big deep like I think you covered this
Yeah, because I think eventually it's all about in some sense eventually it's all about efficiency. At least one of the reasons is that you do this, then you can have a lot more total number of parameters, but your compute at the inference time or the training time is still somewhat small, controlled. Right? For example, if you have 30B active 3B, even though you have 30B parameters, but your computation is only 3B for each of the sequence. So you can have like smaller compute, but still a lot more parameters.
But then, what do you mean, like, because there's another model which is routing, doing the routing, you never know which one is going to get activated. What if you have to still load data if you want to, or?
Yeah, but that's only memory, right? So you only load them in the memory, but you don't have to do the actual compute. So if you are compute bounded in the test time, then this is a benefit. For example, if you do a full dance, like the standard kind of like, suppose your parameter is 1 trillion, let's say. I think this, and it's not a mix of experts, just 1 trillion literally. I think there's almost no chance to serve it in real life because your latency for serving the model will just be way too long, and also the cost of serving the model will be too expensive, and your model, the API, the price on your website becomes really too high so that nobody uses it. So that's why a 1 trillion non-MOE model is just almost impossible. But if you do 1 trillion parameters, but you have active like maybe 30B, then that's like more like a 30B model. But you still enjoy the increase of the number of parameters. Okay, so we have 20 minutes. I think that's probably enough for the rest of the things, which are somewhat easier. So now I'm going to move on to a few ways to kind of like adapt or use the large language models for different use cases, like downstream. So let's say you have already pre-trained your large language model, and now you want to use it for a downstream data set, maybe sentiment analysis, maybe computing some kind of like doing some of your tasks, right? So what are the ways to do that? So some of these, may sound a little kind of like out of date, but they are still useful in various cases. So one of the ways to do it is so-called in-context learning. So let's say suppose you have a new a downstream task. Let's say you have some examples like x1, y1 up to x and yn. This is a downstream task. You have already trained your large language model. And how do you try to make sure your models can predict y given x, right? So that's my question. And the way people do it with in-context learning is that you literally just concatenate all of this into a sequence of tags. So you just concatenate. And sometimes with some kind of like, actually concatenate is a little bit kind of like, maybe let me just be explicit. You concatenate with some format. For example, you can say a question Q. This is literally the string you send to the large language model. You say a question Q and your x task, x1, and then you say a semicolon y1, and you just keep doing this. So for example, in the you can do this. For example, this is an example that is kind of interesting. So you can say Q2 3 is equals to question mark A5 Q6. Let me write this down, and you can see. Okay, so now you have a few of these kind of cases, and then you have Q15 2, and this is your test example. This is X test. Everything above it is training. This is training, so-called training, like our in-context training. And okay, so abstractly speaking, you just write the X test at the end. And then you have A, and you hope it will fill in the numbers you want. So in this example, I think you are all humans, you can probably guess what this should be, right? 2 tilde 3, 5, 6 tilde 7, 13. Right? I think most people would guess 17, right? Because this seems to be, you should interpret this as plus. So that's the learning part, right? You are learning what this symbol means. And most people humans can somewhat guess, not exactly right, but somewhat guess that this is plus. You learn plus from 2 examples, and then you can, when in the test time you guess, it's actually plus, you guess 17. And it turns out that the models can do that as well, from showing a few examples. So of course, these days, doing this is kind of like you should just tell it you don't have to actually learn this kind of simple plus. Then but there are some of the other use cases could be like, for example, if you want to do sentiment classification, or maybe you want to classify your messages into, suppose you have an email, you want to classify it into billing, technical, and accounting, something like that. You want to classify your emails into different things. And what we can do is that you can say, this is another way to write your kind of like a future learning prompt. So you can say classify my messages into, maybe let's say A, B, C. I'm even making it harder. I say I have 3 classes, A, class B, and class C. I didn't even tell it what the class means. And then I have example 1, which is like a message, which is like a message 1. And then you say the output is A. And you have another message. And then you say the output is B, so on and so forth. And you give a few of these examples. And then in the test time, you just prepend some more message. And then you have an output. And then you ask the large language model to fill the blank, right, to generate the next token. So all of these are pre-filling, and this is like to generate. Right? So and what the language model can do is it can figure out what A and B means from these examples. It'll figure out, oh, A seems to mean that it's a billing email, and B seems to means that it's a technical, maybe like a customer service email, right? And then eventually it will give you the right label. Of course, in most cases, people don't actually hide this. Even you hide it, it can work. But the more expensive way is that you just actually tell it. You just have say this is billing, and this is like technical. You make it even easier for the language model, and then the language model will learn it even easier, and it will probably actually sometimes it's also subtle in the sense that maybe you have to kind of like, what's the definition of billing is kind of like a little bit kind of subtle. Then the models can learn from these examples, what are the definition of billing emails. Because I've seen a few examples of billing emails, and then you see, oh, this is like average email like with this kind of format or with this type, I will classify them as billing emails. So in some sense, it's kind of like very similar to teaching people through examples, right? If you want to teach somebody what's the definition of billing, what's a billing email, what's a customer service email, you show them examples, and they will figure out, how to do it afterwards.
I mean, this seems like you can basically do anything like we don't need any model at this point because like you can do like a math equation like with a value. I mean, anything to that is fixed.
If you can teach with examples, yes.
Yeah, like
but actually, you'll see even in the next part, it might be even easier than this. But yes, in theory, you can teach everything like this. You don't have to even. So and here, one very important thing is that you are not updating the parameters of the model. You are only giving the examples in the context, right? As a string to the model. The model is not updated at all. So there's no sometimes the fundamental intelligence is probably not, if you believe that the intelligence comes from the model parameters, then the model parameters are not updated. So in some sense, if you believe that's the case, then it shouldn't really improve the fundamental capabilities by that much. It's more like you are learning the styles or some simple definitions to some degree. Of course, you can also learn some of the hard ones, but how hard it is, is, for example, if this is like suppose this message is like let's say it's biomedical images, right? Like something like you have a scan and you want to classify whether it's a cancer or not, something like that. I don't think showing a few examples can work. You still have to do some tuning.
In this case, are we not training because
we're not training anything, right? We are just prompting it. Right. So a more extreme version is that you can prompt it without even few examples. You can just tell it what is the task, right? So you can just say, you just erase all of this. You just say classify messages into billing and technical service, so on and so forth. And then you probably define text. Like you just describe what each of these labels mean in text as much as possible, but you don't show any examples at all. And that's called zero shot. So zero shot means that you just have a task description. Sometimes the task description can be long, and then you just let the model generate the answer. That's it. So just give the task description, and then the model will keep generating. And that's it. And sometimes you can tell the models what's the output format you want. Maybe you want some JSON output, you want some structured output. You just say, please generate in this format. And then you just, it will generate. And that's probably our experiences with using ChatGPT, right? I feel like nobody really gives them few shot examples these days anymore, except very special cases. And you can just do zero shot. So, and I think this is one of the biggest findings that from the few shot and zero shot capabilities, one of the biggest findings from the GPT-3 paper, because this is kind of surprising because you never update the model parameters. So for people who didn't see the GPT-3 paper, when I was working on it, it's very shocking because we thought that you have to actually train your models on the new tasks a little bit at least. But now you don't have to train it in a standard way. You just have to prompt it. And this in sometimes fundamentally change the convenience or the ease of applying these models in industry, right? So in the old days, if you want to solve some problems in insurance companies, what you do is you say, oh, I'm going to collect a lot of data from this domain, and I label them. I build a dev set, I build a train set. I try to train my models on the dev set. Maybe you start from initial checkpoints, right? You don't have to really start from scratch, but still you have to train on the domain data for a bit and update your parameters. And you serve a specialized model because your model parameters are already updated. You serve a special model in that enterprise, in that company. And then you have a new model in another company. You have the whole process. You have the data set, the training set, test set, and you train a little bit, you tune the hyperparameters, and then you deploy a separate model in the other company. So every model has their own, every company has their own model, and it's much complicated deployment process. But now, you don't have to do any of this. You just have one off-the-shelf model, and each company just writes some of their own prompt. And sometimes there is some scaffolding these days if you do the agentic task. But basically, they just do very lightweight customization by writing the task description, and sometimes giving a few examples. Sometimes you define a complicated workflow, like you have a menu. You have a kind of like what is called like the like if some employees join a company and they sometimes have an onboarding doc on what's the right workflow they should follow, and you just dump those onboarding docs to to the model, and the model will follow instructions and do some of those. Yeah.
Is there like a threshold on how big the model needs to be for this context learning to work? Like, I'm guessing a very small model, like.
This was a very hot topic at some point. We call this emergent properties of the models. So if you go back like 3 years, 4 years ago, I think when people started this, they say, these capabilities start to emerge after a certain scale and certain amount of data. I think that's still true, but these days you can get these capabilities with even small models by, in some sense, distilling from the large models, right? So once you see the capabilities with the large model, then you can always try to distill the capability to the small model. And also, these days the pre-training and mid-training data becomes much more complicated. Actually, this relates to another thing I'm going to discuss next. So in the training data, actually, there are this kind of data already now. So in the old days, the pre-training is just a bunch of kind of like text on the web, but now, at least in some stage of the training, maybe not exactly pre-training, you have data like this. So you can get these capabilities with even smaller models. So maybe actually that's a good segue to talk very, very quickly about how to at least reinforce or how to strengthen the capability of this kind of zero-shot learning and in-context learning. So at the very beginning, they arise naturally. And it's kind of like a surprise. Somehow nobody actually trained for these kind of capabilities, but it actually works. And then people try to strengthen or reinforce these kind of capabilities. And the way to do it is kind of like a relatively easy. So you just do some kind of like a SFT, and people call it instruction tuning. So what you do is you collect a lot of data sets with this kind of format. So you have a data set, let's call it, maybe like I guess let's still call it x I, y, I. And where x is this instruction or task description, they are the same thing. And y is your answer. So, and then you get a lot of this. And then you just continue train your model from the existing checkpoint. You take an existing checkpoint and you train your model to have this behavior. So basically you just say, I'm going to have a loss function where I want to, so maybe let me see, how do I, let's say x is from 1 to, say, what's my notation here? Sorry, just give me 1 second. X is 1 to t, 1 to IOI. There are IOI tokens in X, and there are, say, TI tokens in Y. Your X is viewed as seen, right? So you don't have to actually predict X. X is the instruction. But Y is what you want to predict. So basically, you just say, I want to minimize the log likelihood, minimize the negative likelihood of seeing P, the chance to see P, Y, to see Y from 1 to TI, given XI. Right, and basically you just minimize this loss function. And here you're minimizing over I from 1 to n. You have all these examples, and you normalize by 1 over n, let's say. And this log likelihood, as we discussed, you can decompose it into per step loss functions because this is a sequence, So you can decompose this into a sum over the time step t from 1 to ti and log of the p theta yt I given xi and y less than ti. Right, so you say, given the instruction and given the first t minus 1 token, you want to predict the tth token. And you just sum up the loss functions. And that's it. I think there's some normalization here, like you need to normalize in together, which you can see in the notes, but that's a small minor detail. So that's pretty much what you do. So you just collect a lot of data like this with the task description and the answer, and you do the SF, generally this technique is called supervised fine-tuning. So anything that looks like this is called supervised fine-tuning because you are giving some supervisions, which are the Ys, and you are fine-tuning because you are taking as initial checkpoints and fine-tune. And instruction tuning is the type of supervised fine-tuning where the data set is exactly this kind of instruction type of data set. In some of the other cases, you can do supervised fine-tuning with other kind of data sets as well, of the same form of the loss function, but your data set could be a little bit different.
Doesn't this loss function encourage the model to just follow the direction that the human does? What if the model finds a different method of the answer? Then the model would be discouraged from trying different methods, right? Since it would follow like this label, right?
That's exactly right. In some sense, you probably don't have this data set is mostly designed for letting the model to follow the instructions that the human specifically mentioned. So you are so I think we need to specify what is the so-called instruction, like when you say the models find a different way to solve the problem. Yeah, so but let's say the human's instruction is to solve the math problem for me, right? So no matter how the model solve it, it's kind of fun, right? So but how to solve the model is not part of the instruction. How to solve the problem in the math problem is not part of the instruction in this, right? The instruction is mostly specifying what's the task. And sometimes the humans have some preferences. For example, they say, I want to solve this task in this fashion, or I want my answer to be presented in this fashion, right? So those kind of a requirement are typically the instructions. But the instructions are typically not something like you should solve your math problem with this equation or something like that. Does it make sense?
What if you do a chain of thought, let's say the model does the working out of the math, but that's in the Y, right? Mm-hmm. To that extent, still they would be encouraged to follow the Y that the label was, right?
Yeah. So that's why actually it's not going to work really. If you just depending on how you get a chain of thought, right? Suppose this Y has chain of thought, I guess we haven't discussed it, but suppose Y have chain of thought, it depends on, I think typically these days people are saying like this chain of thought cannot be, like ideally it should be also generated by model itself, right? If human write a chain of thought, then you could have this situation that the models want to solve the problem in some different ways, but humans is kind of like too much micromanagement in some sense. I think it can still help than nothing. Like some micromanagement could be better than nothing, but it wouldn't probably be as good as doing the RL stuff, like so that you can, yeah. We still have one. Oh, wait, we still have like 1 minute and 30 seconds, right? Yeah. Any other questions?
Weights somewhere in this?
In here? Yes, we are. Yes, definitely we are. Yes.
Okay, so this is not some person going into ChatGPT and typing something and giving this in here.
No, this is in the training phase. So basically, the model that ChatGPT delivers to you already had this instruction tuning there. So they collect a lot of instruction data, instruction answer pair data, and they tune all of those, and then they give it to you. And when you use it, they don't actually use your data to train, at least not immediately.
At some point, they did ask you which this is for this, which answer do you prefer?
I think that's for another phase, which we will discuss maybe 2 or 3 weeks later after we have some RL set up.
So it's like if you have like a model which is now trained on this big blob of text, and so after that has happened, we do this instruction gradient, which is specified pairs of X and Y, and then do that technique. The second phase is something like that. Like this is like a second phase of the normal training.
I think typically it's the second phase, even though I cannot be really sure how it's really done in the frontier labs these days, because you can also mix some of this into the pre-training phase to some degree, and some of these are done, it becomes kind of more complicated these days.
If you don't have a lot of the fine-tuning data, is it possible to only fine-tune some of the experts or some layers, or is it usually better to fine-tune the whole thing?
I haven't heard of fine-tuning a subset of experts. Maybe there are papers that does that, but generally speaking, I don't know. I think it might still be better off to fine-tune all the experts, but with probably a smaller number of parameters, you can do the LoRa stuff if you don't have enough data. Okay, now we are over time. Okay, thanks.